Mr. Wade, this is BC. Challenge us.
Well, if you wanted a challenge, you sure came to the right place. I mean, BC Calculus is just one gigantic challenge anyway. Luckily, we're doing the easy stuff now. But this is the first real tough problem here. All right. Y prime equals. We just jump straight in. It doesn't have to be set up or anything. Okay. Look at the lead off. Look at the very first thing. Sine. It's a sine problem. Don't worry about the rest of this stuff right now. The derivative of sine is cosine. What happens to the original base? It stays the same. There's your first step, but we're not done yet. The tangent of 7x squared stayed the same. It's supposed to. But we never did address it. It hasn't gone through the derivative process. Isn't that what the chain rule is for? Times the derivative of the original base. Now just wipe the slate clean, okay? Blank your mind and just think, oh, all I have to do is focus on what's the derivative of tangent of 7x squared. Heck, we can even do an aside. The old college method over here. You get an extra sheet of paper in college, and you do a little extra work off to the side, and then you just can toss this extra paper because it's actually not part of your work. All right? So base equals tangent of 7x squared. If it helps you to set it aside, do it. Most of you will do this in your head eventually. But for now, if we could just get the derivative of this base, that would be my chain rule. What's the derivative of tangent from a previous lesson? Let's call this base prime. How about that? Just for some slang. What's the derivative of tangent? Oh, wait. The derivative of tangent is secant squared of the base stays the same. But hold on. We didn't do this when we did tangent last time. There's another dimension today. Okay? Any base that stays the same in calculus must eventually be addressed. We have to take the chain rule of 7x squared, because what's the tangent rule? The tangent rule is secant squared, base stays the same. But then the chain rule in every derivative says go back and multiply by the chain. What's the derivative of just 7x squared? 14x to the first. Okay? You must do that at the end. Now take all this is your chain rule, insert it back into this parentheses up here. So we put secant squared of 7x squared, quantity 7x squared, times 14x, all right? And that is our chain rule. Now, what really throws people, your brain may be spinning right now, what throws people is that the original base was tangent and we took its derivative to be secant squared. And then there was another smaller miniature base of 7x squared that produced the 14x. It's our first double chain. So the chain of tangent is secant squared, and the chain of 7x squared is 14x. So if it feels a little different, a little harder, that's because this is a double chain, all right? A little harder. So just make sure you keep going until every base that stayed the same eventually also went through the derivative process. That's a good way to think about this. Anything that I can simplify. If you left this, I'll give you full credit, honestly. It's just a one-step problem. You just have to remember the double chain. Now, best answer, let's see. Cosine, that's a trig function. Secant squared, that's a trig function. 14x, that's a polynomial. That should really be your coefficient. You put the 14x in the front, and then you just leave all the trig stuff, okay? So 14x cosine of tangent of quantity 7x squared times secant squared of 7x squared. And you will get the occasional long answer like this in calculus. You'll get some that are longer, but that's okay. No problem there. Just go with your instincts. Now for letter F, we've got f of x equals 2 over x squared minus 49. Now, it's a quotient, it's a division. First thing I would think of is, do I need to use the quotient rule? Because it's more work, but sometimes you have to do it. I don't see an x on the top and the bottom. I don't see an x with the 2. If you have a variable upstairs and downstairs, we have to do the quotient rule. I don't see one. There must be a way to avoid the quotient rule and do this easier. Okay, so the second thing I would think when I realize it's not a quotient rule is the easiest kind of derivative to take is number, base, power. I wonder if I could write this as number 2, a base up here, and then an exponent. I think we can. All right, we've mentioned before that x should not be on the bottom preferably, unless you're going to do a quotient rule. If we could get this to the top, so I know my coefficient's 2. I wish this was up here, but now let's think about the exponent. Okay, so what power is x squared minus 49 actually going to? Well, it's not the squared. That's only on the x. That's not on the whole thing. What's the quantity power? There is none. So if there is no quantity power, it is the first power by default. So when you bring the whole thing to the top, it's to the negative first. Now that makes sense. Okay. All right, now we are derivative ready with our number base power. So I'm going to write f prime of x equals, and of course there's the occasionally used very fancy form d over dx, f of x on the side. That's the exact same thing as dy dx, right? dy over dx. Okay, so what is the derivative of 2 base to the negative first? Negative 1 comes down times 2. Negative 1 times 2 is negative 2. Base always stays the same, x squared minus 49. We always drop the power by 1. So negative 1 goes colder to negative 2 degrees times the chain rule. Because every derivative has a chain rule. I'm going to say that so it's just implanted in your brains. What is the derivative of the original base x squared minus 49? The derivative of x squared is 2x to the first, or 2x. And the derivative of minus 49 is minus 0 because it's a constant. There's your derivative. Now, we just have to simplify. All right, here's your final answer. This group to the negative second moves down to the bottom. X squared minus 49, quantity squared, goes from negative 2 to positive 2. And on the top, who's on the top? Negative 2 and positive 2x. And negative 2 times 2x is negative 4x. And that's your final answer. Just that easy. And just like the last problem, we could ask ourselves, is this a quotient rule or not a quotient rule? It is a quotient because it has a division bar right there. Okay. So is there an x on the bottom and the top both? No, there's not an x here. So quotient rule could work, but it would be really, really messy. So wouldn't do that. Okay. So then the next thing, I guess, because this one's sort of unique, based on your primitive instincts, I mean, you've just started derivatives with me, so based on your primitive instincts, you might be thinking, hey, shouldn't we bring the 3 to the front and leave the base the same and then drop that? Yeah, you could do that. But then when you get to the chain rule of the original base that you have to tack on at the end, that gets super messy right there, okay? So this is a really unique one, and there's actually a better way. I'll tell you what I'm trying to get. Let's draw a fraction bar here. You know what I'm trying to get? I'm really trying to get number base power, because isn't that the easiest way to do it if we could? And you know what? If it's not a quotient rule because there's no x upstairs, you pretty much should be trying to get number base power if it's not quotient or product. And so here's the problem. This cube right here. If I took off the cube, it would look like the last problem we just did. With the cube on it, that's causing a problem. Do you remember in integrated 3 how to cube a fraction? Or square a fraction? Or any power of fraction? Don't you just cube the top, cube the bottom, right? So 3 cubed is 27. And x squared minus 5 cubed is just x squared minus 5 quantity cubed. You can't distribute an exponent across subtraction or addition. So don't even try to cube 5 and x squared. You can't even physically do that anyway. Okay? So be careful there. So quantity cubed, and we have that fraction, and you know what? That is a huge move right there. That is your breakthrough. Because now you can bring this up to the top and write 27 times x squared minus 5 quantity to the not third, but now negative third. Now that is number base power. Now we can take an easy derivative. Instead of that form or that form, none of those are good. That's derivative ready right there. So it's just about getting your instincts. So now we go to y prime equals, all right? Should be pretty simple from here. It's just in the rewriting where the challenge is. The negative 3 simply comes to the front and multiplies the 27. All right, no calculator on the first test. Isn't that a Mr. Wade tradition, right? Doing all the tests without calculator so that you get super sharp. Plus I gotta fix your COVID brain. You're probably a little rusty. A negative times a positive is a negative. 3 times 27 is not on the times tables, but this is one of the few off the times tables that you must know because it comes up a lot in calculus for whatever reason. 3 times 27 is actually 3 times 3 times 3 times 3. It's 3 to the 4th is what it is. 3 times 27 is 81. You can also think of it as 9 times 9 because that's what's actually hiding in there, okay? So commit that one to memory if you didn't already know it. Base stays the same. New power drops by 1. Negative 3 minus 1, negative 4 times the chain rule. Or derivative of the original base, x squared derivative is 2x to the first minus 5 becomes 0. You've got your derivative. Now clean it up. See if we can get a final answer here. We'll need a fraction bar, yeah, because I see a negative power. So this term goes to the bottom, becomes x squared minus 5 quantity to the 4th. And this stays on top, that stays on top, but it's a monomial times a monomial, so you can multiply those. You should multiply those. Double 81 is a 16 and a 2, so 162. And you keep the negative. So negative 162 with an x on the side. And we're done. See you in class. In the last problem, get it straight. Now, if you don't believe in the chain rule, well, you're pretty much going to... 7 times 3 is 14.